All right, we've made it to the end of the story problems for logs and exponential functions. So with level 5.8, we're going to be talking about exponential growth and decay. So these are your sciencey applications. And then the next part will be on Newton's law of cooling, which is a third application for exponential growth or decay. So let's first talk about like populations or heat or other things that have these properties of growth. We have this formula of A of t, or the amount, is equal to A sub 0, which means the starting amount. So again, we have that number in front, which is our starting amount, times e to the kt, where k is our rate. If we are growing, then k is positive. If we are decaying or shrinking, then k is negative. Those are the two main things that I want you to be paying attention to with exponential growth or decay. Is the exponents positive or are the exponents negative? So you can see uninhibited growth we have, and don't yell at me, the book changes the variable when it's talking about these different things. So n of t equals n sub 0 e to the kt, where k is positive. If the growth coefficient is positive, then it's getting bigger. If it's negative, then it's shrinking. So let's just look at an example and see if we can understand this. So a colony of bacteria grows according to the law of uninhibited growth by this model, where n is measured in grams and t is measured in days. So this is important that we're talking about days. Determine the initial amount of bacteria. So the initial amount is, if we use the notation, 100, because that's our number in front. What is the population after 5 days? So what is the growth? Oh, sorry, don't skip the questions. What's the growth rate? What's our k? So our k is this number right here. So 0.045. What's the population after 5 days? We have n of 5 equals 100 e to the 0.045 times 5. So we go back to our calculators. We have 100 times e to the 0.045 times 5. And we get 125.23. 125.23, and this is measured in grams. So we can write grams. We can write grams for A. How long will it take for the population to reach 140 grams? So that's saying 140 equals 100 e to the 0.045 times t. So in order to solve this, we first divide by 100. So we get 1.4 equals e to the 0.045 t. Next, in order to switch this to exponential, we're going to take the log of both sides, and since this is e, we're going to take natural log. So ln of 1.4 equals 0.045 t, because the ln of e is just 1. So the last bit, divide by 0.045. So we get t equals ln of 1.4. Let's make sure that I'm typing that in right. ln of 1.4 divided by 0.045. So if we did that right, we get 7.47 days. And if you want to round that up, you can. 7.48 days. Close enough. So last up, E. What is the doubling time for the population? So if we have 2a equals, so for it to double, if we're starting with 100, it's going to be 200. And again, this is a time question. This is E. So we get 2 equals e to the 0.045. T, take the natural log of both sides. We have the ln of 2 over 0.045 equals t, just to speed things up for you guys. So I can go back here, and I'm just going to delete 2. So it takes 15.4 days in order for this to double. So these are the types of questions that you could expect for growth. Let's flip it over and we're going to talk about decay. All right, so example 2 is another bacterial growth question. So it says, first write the formula. If n is the number of cells, t is the time in hours, express n as a function of t. So we're going to have n equals n sub 0 e to the kt. So that's what we're starting with. B, it's going to give us some initial information. If the bacteria doubles in 3 hours, so 2 equals e to the k times 3. So our doubling, so this is 2, that's 1. Solve for k. So we would take the natural log of both sides, equals 3k, and then divide by 3. We get k equals ln of 2 divided by 3. Control Enter, we get 0.231. So 0.231. So find the function that gives the number of cells in the culture. So then C, how long will it take for the size of the colony to triple? So instead of 3n to the 0.231 times t, because we're looking for t now. So the n's cancel. We have 3 equals e to the 0.231 times t. Take the natural log of both sides. So we have the ln of 3. Hopefully this is becoming transparent to you guys now. Divide by 0.231. So t equals ln of 3 divided by what we got before, 0.231. So we got 4.755. 4.755. And then our time is in hours. So then D, if it's asking you how long will it take for it to double again, so if we already knew that it took 3 hours to double one time, how long is it going to take to increase 4 times? So I'm just going to short this, because this is 2, this is 3, this is going to be 4 equals e to the 0.231 times t. So ln of 4 over 0.231 equals t, if we're just simplifying those. So then let's add a calculator. We're going to do ln of 4 divided by 0.231, and we get 6 hours. So pretty close to just doubling our time. We quadruple, which makes sense. Okay, so the last one, uninhibited decay, radioactive decay. So this happens with elements. There's a couple other things. They also use it for carbon dating. We use the decay that we know how long something that carbon has in it to figure out how old it is. So still same formula. Traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount carbon-14. If the half-life of carbon-14 is 5,600 years, approximately when was the tree cut and burned? Okay, so we first start off with our formula. A equals A sub naught e to the kt. What do we know? Well, first off, we know that it takes 5,600 years to have half of this. So if we have half of the stuff left after k times 5,600 years, we're going to find our rate first. So the a's cancel. We have 1/2 equals e to the 5600 k. We're going to take the log of both sides. So we have 5600 k equals ln of 1/2. So k equals ln 1/2 over 5600. Now I'm going to just round that for you. Ln of 0.5. Let's make sure I type that. Ln 0.5 divided by 5600. That's our k. So our k is negative 0.000123. Negative 0.000124. Okay? So now it's saying, this is what our first part is. How old, if they found 1.67% of the original amount, how old is it? So, okay, so we have 1.67% is 0.0167 is the amount they found, equals the original amount times e to the negative k, or to the k times t, where our k is this. So the a's cancel. We have 0.0167 e to the negative 0.000124 t. Take the natural log of both sides. Hopefully this is not getting redundant. So we have ln of 0.0167 equals negative 0.000124 t. So then t equals, if we divide those sides, I'm going to say this is the ln, ln of 0.0167 divided by, here's a fancy way of doing it. It's going to call back the answer that I just had. And if I hit enter, I get by years. 33062.4. 33062.44 years old. So this is how, when people say, okay, carbon dating, we use the half-life of carbon-14 to figure out the trace elements, and we can make this estimate that it's approximately this many years old. This is the math that they're doing behind that. All right, so we have one more thing to do. If you want to try these problems out before we moving on to Newton's law of cooling, that would be great. So the last two types of story problems that we deal with exponential functions and logs. One's called Newton's law of cooling. The other one are logistical functions. I want to expose you to these, but if you don't necessarily understand them as well as you do growth and decay, that's okay too. Okay, so in essence, Newton's law of cooling is this formula. It says U is the heated object, the temperature, at a given time, given this. So this is our function of temperature, where T is the constant temperature surrounding the area, U sub naught is the initial temperature of the object, and K is a negative constant, which means it's going down, which means it's cooling down. So let's see if we can use this formula. So an object is heated to 100 degrees Celsius and then is allowed to cool in a room whose air temperature is 30 degrees. Okay, so before we even get started, it's heated to 100 degrees, so U sub naught is 100. The temperature on the outside, the T, is 30 degrees Celsius. Okay, what's the question? If the temperature is 80 degrees after 5 minutes, when will the temperature be 50 degrees? So let's see if we can use our formula here. So first off, let's write this out. U of T equals, where our temperature is 30 plus 100 minus 30. Okay, so that's something. E to the KT. We don't know what K is. So we have U of T equals 30 plus 70 E to the KT. That's our formula. Okay, what's the first piece of information? The temperature, our output, is 80 degrees. So we are at 80 after 5 minutes. So that's K times 5. So if I subtract 30, that's 50 equals 70 e to the 5K. So we have 5 over 7 equals e to the 5K. Now I can take the natural log of both sides. I'm left with 5K equals the ln 5/7, or K equals the ln 5/7 over 5, which is, just so we don't have to worry about that, the ln of 5/7 divided by 5. Control Enter, and of course I get a negative constant, which is what I want. It is negative 0.0673. Okay, so now we can use that. When will the temperature be 50 degrees? So the second part, which I'll do in green, is saying, okay, 50 equals 30 plus 70 e to the negative 0.0673 times t. Solve for t. So this is 20 plus 7, so 20 equals 70 e to the negative 0.0673 t, because we subtract 30, divide by 70, so you get 2/7 equals e to the negative 0.0673 t. Take the natural log of both sides. We get ln of 2/7 equals negative 0.067 t, so 3t. Divide by this, negative 0.0673, divide by negative 0.0673. So I'm going to just type this into my calculator. I have the natural log of 2/7 divided by negative 0.0673, or I could have done second answer, and I hit Control Enter. I get 18.61 minutes. Likewise, it says determine the elapsed time before the temperature of the object is 35 degrees. Okay, so I'm going to do this in purple, B, and sorry that I took all this room for A. I want to know temperature of the object is 35 degrees. So 35 equals 30 plus 70 e to the negative 0.0673 t. So this is 5, subtract 30, equals 70 e to the kt, just so I can save my sanity. So we have 5 over 70 equals e to the kt. Take the natural log of both sides. So I have ln of 5 over 70 equals kt. So ln of 570 over k equals t. Okay, so just to save myself some time, I'm going to hit Enter. The top value is 5. Oops. Bottom value is 70 over our approximate k value. Hit Control Enter. I get 39.21 minutes. So it takes 39.21 or 0.21 minutes to cool down from 100 degrees Celsius to 35 degrees Celsius, so almost room temperature. So this is another sciencey application. If we flip it over, we're going to talk about logistic models. So the very last thing, logistical models. I just want to expose you to these. So this is talking about either populations of growth where they start growing and then decaying, which is interesting when you have a negative exponent in the denominator. So let's just look. This is the growth model growth model in terms of time, where A, B, and C are constants. C is bigger than 0, so it's positive, and B is bigger than 0. And the model is a decay model if B is less than 0, because if B is less than 0, then that's positive. So this is our growth model, and this is our decay model. So I just took these facts to describe the logistical model. You can obviously read through them. The domain is all reals. The range is from 0 to c. There are no x-intercepts, and the y-intercept is our initial amount. There are two horizontal asymptotes, which is pretty interesting. There's a lower bound and then there's an upper bound. So the other interesting thing happens, which we call an inflection point, which it starts from increasing to decreasing. And that happens at the halfway point when we get half the amount. So it's not always halfway here, but it's halfway up. And that's where it changes from increasing to decreasing. So inflection points is where you start reaching capacity. This is for businesses, for population growths. So if we're talking about the U.S., what's the logistics for the U.S. population to keep growing and growing and growing? Well, eventually there's not enough houses for people to move into. So the logistics of having so many people becomes at the upper end. China is experiencing something like this right now. So with example 2, fruit flies are placed into a milk bottle with a banana for food and yeast for food and to provide them to lay eggs. Okay, that's a little too much information. Suppose that the fruit fly population is given by this logistical model. State the carrying capacity. So what's the initial amount? So carrying capacity is what's your C. So C is 230. That's not that bad. What's the growth rate? Our growth rate is 0.37 or 37%. Now you might be saying, why is it 37% growing and not decaying? Well, because the B is positive and our exponent should be negative to begin with, we are growing. But if this was positive, then we would be actually shrinking. So this is a positive number here. Determine the initial population. Okay, so what happens at 0? So when t equals 0, what is the initial population? So here's the nice thing about formulas. All you have to do is plug them into your calculator, and it does the work for you. So 1 plus 56.5 times e to the negative 0.37. And t is 1, so I can write times 1. So our initial population is 5 point, let me say that, oh, sorry, t is not 0. Oh, sorry, t is not 1, t is 0. Good catch, Mr. Swenson. So t is 0. So our initial population is 4. What is the population after 5 days? Okay, I just go back to the formula I typed in. Change the time from 0 to 5. And it's 23.27. Well, you can't really have 0.27 flies, so our population is about 23 flies. How long does it take to reach the population of 180? So we're going to set 180 equal to 230 over 1 plus 56.5 e to the negative 0.37 t. I'm just going to flip-flop these. I have 1 plus 56.5 e to the negative 0.37 t equals 23 over 18. Subtract 1, subtract 1. I've got 56.5 e to the negative 0.37 t equals, let's just do 23 divided by 18 minus 1. So just so you see, that's 5 out of 18. If I just divide by 56.5. So I've got e to the negative 0.37 t equals, okay, we're just going to we get 0.00491. It's important that we don't round, but if we do, 492. We're as close as possible. Okay, so now take the natural log of both. So now I'm just going to take the natural log of that answer. We get some number. So we get that is equal to negative 0.37. T equals negative 5.315 divided by negative 0.37. I'm going to take this, divide by negative 0.37, and I get 14.365. And what's our time? Days. So T equals 14.365 days. Hopefully this is just a little bit of an exposure to story problems, especially going back and forth between exponentials and logs. And you can kind of see that anything that's growing exponentially or decaying exponentially is pretty useful.